Okay, so now we go to a question with a couple of charges, and we still need to be able to find net field, so that's us, and this now new net potential. All right, so net field we already know how to do. You'll notice that I picked some distances, I picked some charge values just so we could find an answer. All right, so, so
I'm not gonna be able to go. Actually, I got.
So net field, I'll start by drawing from this Q1. There's a field at location X that looks like this. We'll call it E1. At that location, there's a field from charge 2 that looks like this. I'll call it E2. All right, and we know that to find the net field, we're going to have to do the Pythagorization of those two. See there, buddy? Of those two fields. Okay, so I'm going to write that as, let's see, KQ1 over R1 squared plus KQ2 over R2. Oh, I forgot this squared, and squared, right, because that's our Pythagorean theorem thing. Okay, so let's do a little subs and a little solving. You go. All right, so I get that the net, I get that the net field is, let's see, we'll call it 8.04 times 10 to the 6th newtons per coulomb. See you down there, buddy.
Guys, see you down there.
All right. Okay, now, I didn't do my substitution, but here, right, electric field vector. No sign in the math. All right, and the reason we say that is because here is where we, in this drawing, is where we take into account the sign of the charge. All right, we use the sign of the charge to figure out the direction of things. Okay, and then once we have the direction taken care of, then we can use that to figure out, how we find or how we make our expression for the net electric field. Okay? Now, net potential. What we're going to do here is, potential is a scalar. It's a scalar. Just add them up. All right? But here, we have to use the sign. All right? So the convention I use, what I've gotten used to over the years is the fact that when they're dealing with vector quantities like force or electric field, you don't use the sign mathematically. You use it to figure out direction, and then you use those directions to figure out either net force statements or net field statements. When you're using scalars like potential or potential energy, well, what you do is you do use the sign of the charge. Okay, so here we just do literally KQ1 over R1 plus KQ2 over R2. All right, if you'd wonder where that expression for potential came up, or where we came up with that, just go to the last page, or a couple pages ago. Okay, so the big deal here, notice that we have a negative here, so we have to use that negative in our Q2. All right, so I will write this one out. So I'm going to do, how about this? I'll factor out the K. I'm just going to leave it as K. Q1, 2.0 microcoulombs. Of course, you'll change that to 10 to the negative 6 coulombs. And then I'm going to do this, watch, minus 5.0 microcoulombs. All right? We're really saying here plus negative 5.0. Okay? Oops. Square brackets. Okay, of course, change these to meters. Of course, change those to times 10 to the negative 6ths. All right, and let's do this. Let's see, 2e negative 6 divided by 0.15 minus 5e negative 6 divided by 0.075 times 9 times 10 to the 9th. And I get a potential of negative 4.80, let's call it, times 10 to the 5th joules per coulomb. A negative potential. Now that does not mean potential is to the left or anything like that. All right, it means the potential is negative. Okay, and we're going to talk next time about why potential could be negative, what it means physically. What I think is just some of the best physics we do this year that talks about, oh yeah, that makes sense that potential is positive or potential is negative. Okay, so we'll get some good practice on Monday right off the bat with finding net fields, well, really net potentials from different charge distributions before we get into this next stuff, electric potential difference, right? Here we're talking about electric potential. Next we talk about electric potential difference, okay? I hope that'll do it, folks. And let's see, for Monday, don't forget, finish your lab, finish those electric field problems, and get on these notes. Not too bad, about 20 minutes of notes. Hey, block 1, I screwed the, never mind, I made a mistake here. I was so excited about me saying, hey, field is the same as acceleration that I just wrote that I wrote this, acceleration is E. That's just plain old not true. All right, we derived this on the last page here. All right, there's our expression for acceleration of a charge. Acceleration of a, well, here, acceleration of an electron. Here, we just say, more generally, here's the acceleration, get rid of this. Here's the acceleration of a charge in a uniform electric field. It certainly depends on the mass of the charge and the charge of the charge. Okay, so sorry about that mistake, but make sure you are comfortable with that. Okay? All right, folks, happy weekend. See you.